All right, good morning, everyone. And as I was announcing, I'll be talking in the next two talks about joint work with Baptiste Morin from Bordeaux, and which will switch the point of view from motivic L functions to zeta functions of arithmetic schemes. And the original motivation for this project came from ideas of Lichtenbaum on what he called Weil-etale topology, but the ideas have evolved, and as I will be explaining, they look a little bit different than originally intended. But at the origin of all of this is really ideas of Lichtenbaum. So throughout X has the same meaning. We have a regular connected scheme of dimension D, proper over the integers, so some nice arithmetic scheme. And we have its zeta function, which is a very simple construction, just given by the closed points in Euler product. And so again, one assumes that it can be an meromorphically continued to any complex argument. And then one wants to describe the vanishing order and the leading coefficient, which is a real number. And so this setup, as you might notice, includes proper smooth varieties over finite fields, which the motivic formalism I talked about before does not include. The generic fiber of X will be a smooth proper variety over Q, as considered previously. Okay, so let me start with the case of finite fields. And this was first considered by Lichtenbaum, and let me try to explain, to make clear what this idea of Weil-etale cohomology or the Weil-etale topology is. So we have a smooth proper variety over spec Fp. We want to describe this special value at S equal n in terms of this motivic complex, which is rationally a weight n piece of the algebraic K groups of X, but we're interested in the integral groups to get really the L value up to sign. And over finite fields, one has a choice. One can understand this complex Cn to be constructed as from the higher Chow complex, which I will explain a little bit more later today, or one can use a rather different construction, but still also related to algebraic cycles by Suslin-Voevodsky. So either is a complex of sheaves on the etale side of X, and in low weights, they look very simple. So Z0 is just Z, Z1 is the multiplicative group shifted. And so inside the Galois group of Fp, which is a Z hat, one has the Weil group canonically generated by the Frobenius, which is just a group Z. So the simplest case would be spec Fp itself, a point at n equals 0. And if you look at the Galois cohomology, you compute it, and it's Z in degree 0 and Q mod Z in degree 2, and 0 everywhere else. So you get not only finitely generated groups. So this is kind of the key problem. If you take the etale cohomology of these motivic complexes, you get finitely generated groups in some degrees up to a certain point. And then in higher degrees, you get co-finitely generated groups like Q mod Z. And Lichtenbaum's idea was that this can be modified by replacing the Galois group with the Weil group. Namely, if you compute the cohomology of the Weil group, which is just Z, so group cohomology of Z, I guess everybody knows if you have taken any class on group cohomology, it's just a Z in degree 0 and 1. It's the cohomology of a circle, the classifying space of Z. And going one dimension higher, if you have a smooth proper curve, and for a change, let's look at n equals 1. Again, you get the cohomology of the multiplicative group shifted. So in degree 1, you get the units. In degree 2, the pK group, which is finite plus Z because it's a proper curve. And then again, in some higher degrees, you get co-finitely generated groups Q mod Z. Whereas if you take the Weil group, so you can kind of replace the etale side with what Lichtenbaum called the Weil-etale side, where you simply adjoin one object to the étale side, which has covering group Z, and which covers all the finite extensions, so it maps to the Z hat. So you make this somewhat ad hoc modification of the étale side, and you get a new topology, and its cohomology would be finitely generated in all degrees, as indicated in this list. And again, you have the same rank 1 in degree 2 and 3. So that's another thing that's kind of pertaining in general. So you have groups with the same rank in 2 consecutive degrees. Okay, and so so Lichtenbaum's idea was this is much nicer to describe L values, because an L value is a real number, and we don't want to L-identically complete or anything to get rid of this Q mod Z. So we would like to have finitely generated groups in all degrees. So continuing the situation over finite fields. So in general, you would define this Weil-etale cohomology of the motivic complex, for example, by some Hochschild sequence as the Weil cohomology of the usual étale cohomology over X FP bar. And as in the 2 previous examples, one would conjecture that this is always finitely generated in all degrees and of course bounded, so it's a perfect complex. And this is known for dimension less than or equal to 2. Well, yeah, I think it's known for surfaces as well. Anyway, so that's the only thing one has to conjecture. This finite generation is always the deepest part in all these special value conjectures. And then one can describe the L value. And this was started by Milne in the 1980s and then reworked by Lichtenbaum in the Weil-etale setting, and more or less, I mean, only for n equals 0 and then Geyser in general. So one has the following picture, which kind of will pertain throughout this talk. Once you tensor these groups with R, there's a natural exact sequence with a cup product with a certain class theta in H1, X Weil-etale with Z coefficients, which is simply the natural class in H1, which we had on the previous slide. The H1 Weil-etale Z has a natural class in H1, which generates a copy of Z. And so that's the class theta, and cup product with this theta gives you an exact sequence. So that in particular means the Euler characteristic of this Weil-etale complex tensor R is actually 0, because of what I said previously. You basically have the same rank in 2 consecutive degrees. And then the vanishing order is given by the secondary Euler characteristic. So you can still extract the vanishing order from the ranks of these groups, but you have to take the secondary Euler characteristic, like in the second statement. And finally, the leading coefficient is given by the integral Weil-etale groups. So since this makes an exact sequence of real vector spaces, the Z lattice in there given by the Weil-etale groups form, after taking determinants, form a natural section in R, which is just a number. And so that number would be the L value up to this power of P. So there's a correcting factor that was first discovered by Milne, P to the chi xon, which has this formula in terms of the Hodge numbers of X. And so Milne discovered this formula, but he didn't actually give it a meaning. That was discovered much later by Morin, that this is actually an Euler characteristic of a fairly natural complex. But for now, it's just this combination of Hodge numbers that you have to throw in to get a complete formula for the leading coefficient. Okay. And so that's kind of the picture one wants to have in general, even for characteristic 0 arithmetic schemes, but there will have to be some modifications. And so this can be proven. Well, let me briefly recall why. One can prove anything over finite fields. That's a well-known story. of course, you have a formula for the zeta function. It's not just an Euler product by the Lefschetz trace formula. You can express it as a rational function in T, given by the characteristic polynomial of Frobenius operating on Weil-etale cohomology. So that's a well-known story, and you can do that for any prime different from P, and that will give you the L primary part of the zeta value. And it can be related to the motivic complex, because another key property of this motivic complex is that the complex mod L to the nu is just the roots of unity complex twisted n times. It's a basic property of motivic complexes in the etale topology, provided L is invertible, so it's different from P. So that means now that the usual Galois-Weil-etale cohomology of the roots of unity is just the Weil-etale cohomology tensored with the L. So that's a very simple relationship. The Weil-etale groups just give an integral structure on the usual Weil-etale cohomology groups of X. And then for L equal to P, one also has a formula for the zeta function using crystalline cohomology, or the de Rham-Witt complex. And there, the computation to get the special value is a little bit more complicated, and it produces these two terms. So on the one hand, you have motivic cohomology, which also has a P primary part, possibly, but you also have this additive term coming in from the Hodge numbers. So that's why one can prove everything over finite fields. Okay, so to prepare for characteristic zero, let me briefly say what these higher Chow complexes are. So over finite fields, we had a choice. One could take higher Chow or Suslin-Voivodsky motivic cohomology. Over arithmetic schemes, there's only one choice. Only higher Chow groups are defined. So that goes back to Bloch. He had this idea of generalizing the classical Chow groups in the following way. So you have an algebraic M simplex given by this very simple affine space, but with these coordinates T0, Tm summing up to 1. And that makes a simplicial scheme because you have the usual phase maps, just like in topology, by leaving out coordinates or setting coordinates equal to 0 and 1. So that's a simplicial scheme. And so you can take the product of this scheme over spec Z with any scheme Y. And then let's say Y is nice Noetherian. So every point has a codimension. And so you take the free abelian group, a group of cycles on codimension endpoints on this affine space cross Y. But you need the condition that it intersects all the faces properly, so you can make a boundary. It has a well-defined boundary. And so you get simplicial abelian groups from these cycle groups. And any simplicial abelian group you can view as a homological complex. So I will switch between these two points of view. So it starts in degree 0 and then degree 1, 2, but in homological degrees with lowering differential. And the higher Chow groups are the homology groups of this complex. Looks very concrete, but it's very hard to work with this and to prove things with it, although one can prove things using the cycle description, but it's not easy. For example, a localization sequence, famously proven by Bloch after some effort. So now once Y is regular and N is bigger than 0, by some reindexing, we get a cohomological complex, and that's the Zn I was talking about. So you make this reindexing, and all these cycle groups are naturally etale sheaves, so you get a complex of sheaves on any given regular scheme, given by this formula here. And again, it has this key property that modulo L, some power of a prime L, that's invertible on the scheme. It's just the roots of unity scheme, even though it looks so complicated involving all these cycles. Mod L to the nu, it's a very simple sheaf. So it's concentrated in degree 0 in particular, which is not true for the integral groups, only after you analytically complete. And rationally, the etale cohomology of this Zn complex tensored with Q is the same as the Chow groups tensored with Q, so gives back the original higher Chow groups. And they have a spectral sequence to K theory, so you get the weight n eigenspace of K theory. And if somebody remembers, this was also the way these spaces H1F and H1M were defined in my talks yesterday. There were certain Adams eigenspaces of K groups. But here we want to get a nice integral structure, and so we're switching to Chow groups, but in the etale topology. So the problem in the etale topology is the same that one had over finite fields. The groups are not finitely generated in all degrees, even conjecturally. And so I will explain how to resolve that. So just as a reminder, we also need Deligne cohomology, which has no analog over finite fields. It concerns the Archimedean fiber. So again, if we have our arithmetic scheme X, but now flat over C, then the complex points, they make up a complex manifold, compact, with a Galois action of the Galois group of C over R. And then one has the Deligne complex, which in degree 0 just has the constant sheaf Z with this factor 2 pi I to the n, mapping to the structure sheaf, the holomorphic structure sheaf, and then you have the holomorphic differentials. And you take its cohomology on this complex manifold, and then it's GR cohomology. And the same with real coefficients, but so there you take the constant sheaf R in degree 0. So the real coefficient Deligne groups are not the integral groups tensored with R. They're defined in this way. Yeah. And both are needed for L-value conjectures. So if you have any recollections of my talk yesterday, basically you have Betti cohomology in there coming from the constant sheaf in degree 0. You take the plus space coming from the GR cohomology. And you also have the tangent space in there, which is the truncated de Rham cohomology. So there's a comparison to the algebraic de Rham cohomology tensored with R. So we have the natural Q structures coming up in my talk yesterday. They appear again in the Deligne cohomology. So you have the same kind of ingredients. Okay, so as I was saying in the announcement, these special value conjectures, they can be formulated in 3 different ways, in the style of the class number formula, using a fundamental line, or using Weil-Arakelov cohomology groups, which is maybe the most speculative, but I think also the most convincing way to formulate this conjecture. And so I'll start with those Weil-Arakelov groups. So these are the groups which generalize the Weil-etale groups I talked before over finite fields. I just gave them a different name because they're really not quite what Lichtenbaum expected. For example, they're not finitely generated in all degrees, but I think they make a much more convincing picture. So we call them Weil-Arakelov because there is a connection to classical Arakelov groups. Again, X usual assumptions, but now flat over Z. We take Zn, the higher Chow complex, as explained. But the special value conjectures pertain to all integers. So the cycle complex only makes sense for non-negative n, or it's 0 if n is negative. But the special value conjectures are uniform, as we saw yesterday. They work for all integers. And for n less than equal to 0, we make an ad hoc definition of Zn just as the relative cohomology of projective space. So if you take just the constant sheaf Z on projective space over X and take its push forward in the etale topology, it will split into a copy of Z in degree 0 and then a Z minus 1 in degree 2, which is just a torsion sheaf, again given by twisted roots of unity, but twisted with minus 1. And so all the constructions that we do, they work again quite beautifully and completely uniformly for all integers n. with this definition. Okay, again, one has to assume some hard things to get this picture. First of all, we have a finite generation assumption that, again, motivic cohomology, but now in the etale topology, is finitely generated, not in all degrees, as I was explaining before, but only in degrees less than or equal to 2n plus 1. So in degree 2n plus 1, one expects this to be finite. For example, the Brouwer group in degree 3 for n equals 1. And then in higher degrees, the groups should be cofinitely generated. Then how do the Archimedean places come in? They come in via the Beilinson conjectures. So one has the Beilinson regulator map, which I call Cyrillic B, from R gamma x Rn. So this is simply a notation for the motivic cohomology tensored with R. So it's this complex here, the etale cohomology of Zn, but just tensored with R. And on there, one has the Beilinson regulator map to Deligne cohomology, and its mapping fiber we call compact support motivic cohomology. I think this was also considered by Holmström and Scholbach, and they call it Arakelov motivic cohomology, but it's not quite Arakelov groups. Then one can construct a pairing between this compact support motivic cohomology and the usual motivic cohomology in the dual degree and dual twist to R. And so this can be rigorously constructed, but of course, one doesn't know that these spaces are finite dimensional, but it's part of the conjecture that they're finite dimensional and that the pairing is perfect. So it's just a nice duality of finite real vector spaces. Unfortunately, this is only known for Specco F. So some arithmetic duality with real coefficients. And the third assumption we need is Artin-Verdier duality. And luckily, this is not so conjectural. This is actually known in many cases. So once you pass to motivic complexes modulo some integer, again, this would be just roots of unity sheaves if the integer was invertible, but on X, no integer is invertible. It's flat and proper over spec C, so it has all residue characteristics. Nevertheless, this complex is the right thing. And when people have proved dualities for the torsion motivic cohomology of this shape, as I was indicating here. So again, this is not quite known in all cases, but it's known in many cases. If the dimension is at most 2, if X is smooth over some integer ring, or if X is bigger than the dimension or less than or equal to 0. So we need these three assumptions, which are quite reasonable and generally expected, to construct our groups, these Weil-Arakelov groups. And so let me first discuss the groups with Zn coefficients. Again, the idea is that such an arithmetic scheme, even though it's proper over spec Z, it's still not compact. It misses the fibers at infinity, just like spec Z itself. And so we construct complexes associated to some Arakelov compactification X bar, and to some fiber at infinity, X infinity. And then we have this diagram with exact rows and columns, which should remind people of the usual localization triangles in sheaf theory, when one has a decomposition of some scheme X bar into an open X and a closed complement X infinity. Yeah, so this is just, for example, in etale or in usual topological cohomology, whenever you have an open-closed decomposition in a topological space or in a scheme in the etale topology, you get this diagram. So you just have a localization triangle restricting to the closed part, and you have a localization triangle restricting to the open part. And we just imitate that, and we define complexes for all terms in this diagram. And it's at this point too complicated to say exactly. Let me just say we define them all. And of course, unlike in Lichtenbaum situation, you cannot expect them to be all perfect complexes of abelian groups. For example, the Deligne cohomology groups are not. They have, even with Zn coefficients, they have R vector spaces in them. And so do Arakelov groups. So in general, all these complexes, they only live in the derived category of locally compact abelian groups. or you could nowadays say condensed abelian groups following Scholze and Clausen. You could also view it from that point of view. So not all of these complexes are perfect complexes of abelian groups, but the complex associated to X itself is perfect, just like over finite fields. I mean, and just to give an example, if you have spec F and n equals 1, then this complex has cohomology of the units in degree 1, and the Picard group plus this direct sum of Z in degree 2. And if any of the listeners has some experience with Gauss module theory, so that's what people would call a Tate sequence in Gauss module theory. That's a nice perfect complex, even if I consider the group action on such a number ring. It would be a perfect complex of ZG modules. And the groups associated to the Arakelov compactification is the usual Arakelov class group in degree 2. So in degree 1, as one would expect, the units on the compactified schema are just the roots of unity. And then here one gets the usual Arakelov class group that people have studied for a long time. And then we'll get the Z in degree 3, which has no classical analog because people have not looked in the Weil-etale topology for these groups now. Okay, so that's just a brief hint how these groups look like, but we construct them for all X under the assumptions on the previous slide. Now, unfortunately, there's not only Zn coefficients, there's also Rn coefficients and R mod Z coefficients. So for all these terms in this diagram, one has groups with Rn and with R mod Zn coefficients, and they form an exact triangle. So for all of these, there's in fact 2 more groups, and as one would expect, the Rn groups, they're just perfect complexes of R vector spaces, which also live in the derived category of locally compact abelian groups. So again, one can stay in this context of locally compact abelian groups. And again, to give an example, the H2n X bar Rn would be what Gillet and Soule call the Arakelov Chow group associated to X with R coefficients, which is not the group with Z coefficients tensor with R. It's like the Deligne cohomology, there's some modification necessary. Okay, throwing in the assumptions that I had on this slide, one can prove that the dualities for these R n cohomology groups exist, but now the top degree is not 2D, like in the Beilinson conjectures, it's 2D plus 1. Again, one has this doubling up of ranks, like over finite fields. So the top degree is 2D plus 1. And so one has the compact support of X is dual to the usual cohomology of X. And the groups of X bar, they're self-dual, as one would expect. So all this works out nicely. And on the integral level, one has a Pontryagin duality between the group cohomology of X and the compact support cohomology of X and the usual cohomology of X, but with R mod Z coefficients in the dual degree. And on X bar, one also has a self-duality, but between Zn and R mod Z coefficients. On X bar, the groups themselves are locally compact, the cohomology groups, whereas in general, only the complex is a complex of locally compact groups. It doesn't imply that the cohomology groups are locally compact. Okay. So this is why we call this picture of Arakelov, Weil-Arakelov groups, because there is a connection to classical Arakelov groups that people have considered before. Okay. And again, if I have time, I will say a little bit more how we actually construct these complexes, but let me move on. How do we describe the zeta values now? Again, it's a zeta function of X, so one would expect it to be related to the compact support cohomology of X, right? It's still missing the Euler factors at infinity. And so we look at the compact support cohomology of X with Zn, Rn, and R mod Z coefficients, and they have parallel properties to what I was saying for finite fields, again, the real groups are finite dimensional, and there's this exact sequence, and Euler characteristic therefore vanishes, but the secondary Euler characteristic should give the zeta value. So that will be on the next slide. So let me just say then, we need the real coefficient groups to describe the vanishing order. And then the groups with R mod Z coefficients, they always turn out for any n to be compact commutative Lie groups. So they just look like a bunch of products of S of circles and a finite abelian group. So, I mean, one might think this is just the perfect complex of abelian groups. This is the same perfect complex tensored with R, and this is the co-kernel, which would then look like this, right? And the co-kernel would have compact cohomology. And that's in fact true, but only for n less than or equal to 0. For n greater or equal to 1, the story is more complicated. But what is always true is that the R mod Z groups are compact. Yeah, and then the relation to the zeta function is, as one would expect, the secondary Euler characteristic gives the vanishing order, and leading Taylor coefficient is given by the volume of these compact groups. And there, of course, a question immediately arises. What do I mean by this volume? I mean, the fact that they're abstractly compact commutative Lie groups doesn't mean that they have a canonical measure on them. So I have to define with respect to what measure I take this volume. So I have to spend a few slides describing this. So here's the definition of the volume. So first of all, for any locally compact abelian group, one can define a tangent space. There's probably other ways to do it, but you could take the Pontryagin dual of the group and then take continuous homomorphisms into R. It comes with an exponential map, which is just the fact that hom into R maps into hom into R mod Z. But this is the double dual, which is G again. So you have this map from the tangent space to G. And if G is just Z, the tangent space is 0. If G is R, it's R. If G is R mod Z, the tangent space is R. So it's just, as you would expect, what the tangent space is. And so if G is such a compact commutative Lie group, the fiber of the exponential map is a lattice. It's not quite a lattice, it's actually a perfect complex of abelian groups, because in degree 0, it's the kernel of the exponential map, which is a lattice, but in degree 1, it picks up this finite group that might be in this compact group, right? It's not just a torus, it's a torus cross finite, and then this finite contributes to the H1 of this L. So it's not just a lattice, but it's a perfect complex of abelian groups. Okay, so from this compact commutative Lie group, one gets the perfect complex of abelian groups as the fiber of the exponential map. Now, a volume form would be a non-zero section of the tangent space, right? And the volume of this group G would be just the factor which I call vol G here, between the volume form and the determinant of this lattice, which also lives inside the determinant of the tangent space here. So you have two Z lattices in the same R vector space, and so there's a real factor between them that relates them. So the volume form normalizes the measure, and then the measure of G is the factor you need to map the volume form to the lattice. I mean, that's just a long-winded way of explaining the Haar measure on a compact group. But now, in our situation, we not just have groups, we have complexes. So this tangent space functor we can easily extend to the derived category of locally compact abelian groups, and it lands in the bounded derived category of real vector spaces. And then what we call Weil-etale cohomology is just this fiber of the exponential map. And this is now a perfect complex of abelian groups from the fact that the R mod Z cohomology consists of compact groups. So we call it Weil-etale, but it's really not cohomology of any topology. We just call it Weil-etale because one of Lichtenbaum's expectations was that Weil-etale groups are always perfect complexes. And this is indeed what we get from this fiber of the exponential map. But it doesn't always coincide with what I was calling the arithmetic or the Weil-Arakelov groups. So one has to distinguish those two. So this is always a perfect complex for abelian groups. And so given a volume form then, which would be a section of the determinant of the tangent space of this complex, so would be an alternating determinant of the HIs. And of course, I can also view the tangent space of the compact groups as the lattice tensored with R. So I need to produce another section of this determinant of the Weil-etale complex tensored with R. And then the volume, as I was explaining before, is just a unique real number, so that the determinant of this lattice is Z times mu times the volume form. So that still doesn't tell you how I find the volume form. I'm just preparing the ground for it. I have to come up with another section of this determinant here that normalizes the volume. So where do I get this other section from canonically? So I go back to my triangle. So triangle 1 was just the triangle that relates the Zn coefficients to the Rn to the R mod Z coefficients, right? So that was my triangle 1. And I apply the tangent space functor to it. So that's a, and I end up with a triangle in the derived category of real vector spaces. So the middle term stays the same because it's already a perfect complex of R vector spaces, so applying the tangent space functor doesn't change it. The outer term, the R mod Z cohomology, has this tangent space as explained on the previous slide. And then the tangent space of the Zn cohomology, well, I computed from the defining triangle of the Zn compact support cohomology, which was on this slide here. So the top triangle, which relates the cohomology here of X with the Deligne cohomology, or a slight variant of Deligne cohomology. But the Deligne cohomology, even though it has Zn coefficients, has real vector spaces in it, as explained before in the definition. So applying the tangent space here, so this is discrete, this is perfect complex of abelian group, so it has trivial tangent space. So this complex inherits its tangent space from Deligne cohomology. And so that's what I'm saying here. So well, not yet. What I'm saying is I'm applying the determinant of this triangle first. So what's happening first, if I apply the determinant to this triangle, I get an isomorphism between the determinant of this and the determinant of this times the inverse of the determinant of this. But now the determinant of this real groups is canonically trivialized by the exact sequence that I had before, by this cup theta sequence here. So if I take its determinant, it's canonically R. I can leave it out of the computation. So this drops out, and I get an isomorphism between the determinant of this and the determinant of the tangent space of Zn. And now I can throw in my defining triangle that I was already mentioning. So this inherits its tangent space from Deligne cohomology. And Deligne cohomology had this truncated de Rham complex in it with holomorphic forms, but that's isomorphic to the algebraic de Rham complex truncated. And so I at least get a nice Q structure already from algebraic de Rham cohomology in my tangent space here. And so the volume form comes from a Z structure. So the rational structure is already the correct one. It's like in yesterday's talk, it would be the tangent space in the Fontaine-Perrin-Rigaud formulation. It comes from this term here, but we want an integral. We want not only a section up to rational numbers, we want a precise volume form. So of course, the idea is we choose some perfect complex, which is an integral structure of this rational truncated de Rham complex. And Yeah, so that's what I'm saying here. So we want some perfect complex of abelian groups, which tensor Q is the algebraic truncated de Rham cohomology. And then this would define our volume form just by taking its determinant. This would be defining our V. So what would be the obvious choices for P? Of course, we can just take the naive algebraic de Rham cohomology of X over Z. So then, since we now have an arithmetic scheme, X does give a Z structure, but it's not the right one. It doesn't help much. And so one of the first discoveries in this project was that the derived de Rham cohomology actually works much better. So this is a theory that was defined by Ilusy in the early 70s in his thesis. And it was discovered by Morin that if I take X over a finite field, smooth proper over a finite field, this truncated derived de Rham gives exactly Milne's correction factor that I had at the beginning of the talk. So this somehow unmotivated combination of Hodge numbers is the multiplicative Euler characteristic of this thing. And so we try this also in characteristic 0. It looks much better than naive de Rham cohomology. And so taking this as our volume, defining our volume form via its determinant, of course, the special value conjecture becomes something like this, that the determinant of Weil-etale is the leading coefficients times the volume form here, where the correction factor ideally should be 1. It is 1 over finite fields. Unfortunately, it's not always 1 in characteristic 0. It's also 1 if n is less than or equal to 1. But the proof for n equals 1 is quite complicated. But the thing I want to point out here is that one can define a correction factor, right? So, so we want to make a special value conjecture. Of course, throwing in some arbitrary factor here destroys everything. Then we only know the factor up to a rational number. But we can define this factor so that our special value conjecture is compatible with the Tamagawa number conjecture from yesterday, even though it looks completely different. But at least if X is smooth over a ring of integers, there's a fairly direct relation between the two. And so that's what we did. We kind of took derived de Rham cohomology as a best guess for this volume form. And then we throw in a correction factor so that the conjecture is compatible with the Tamagawa number conjecture. So that gives a precise statement, except we cannot compute this thing yet. So after computing some examples, we were actually able to come up with a guess for this factor, which will be on the next slide. And this guess led to a much nicer exact expression for this volume form. It's given by the determinant of a perfect complex, which is another integral structure of algebraic de Rham cohomology truncated, and which I'm also trying to explain, but maybe tomorrow. I don't have the time today. So this is something, as I was saying here, it's the motivic weight n-graded piece of some theory you'd call TC plus of X involving topological Hochschild homology. And with this complex, which is another integral structure in the same rational complex, we get a clean formula without any correction factor. So this is kind of the latest status of our picture. And I was very surprised that there is such a complex which gives a clean conjecture, but again, Morin found it, and it's really beautiful that this works. So again, over finite fields, this again gives Milne's correction factor, even though the natural map between those two is not an isomorphism. But both these complexes over finite fields give Milne's factor. Okay. So let's go back to the situation that we had for most of the project, that we had to throw in this correction factor to make everything compatible with the Tamagawa number conjecture. Again, as I was saying here, forced by compatibility. And then we can compute it in some cases. So it's trivially 1 if n is less than or equal to 0, because there is no tangent space then, and everything works just with the Weil-etale cohomology. So it's a much simpler picture. It's also 1 for n equal 1, but that's a non-trivial computation. Again, over finite fields is also 1, as discovered by Morin. And then I was computing this factor for spec OF, but only if all local fields are abelian. And there it was this factorial. So that was the status of our knowledge for a long time, and then Morin guessed that it should be this in general, this factor, and it turns out this is also the factor that relates this group that I haven't really said much about, but it exists, this TC plus group with the usual derived around cohomology. So the difference between these complexes is just this product of factorials involving the Hodge numbers of the generic fiber. So if X is over a finite field, this is all trivial. The correction factor is, the C infinity here is 1, and they give the same integral structure, the same power of B as in Mills formula. Yeah, so that's our conjecture, except that this factor is not always explicit. Well, I mean, of course, in the latest version of the conjecture, we just use this, and we have a clean formula involving no periodic Hodge theory at all. It just involves this TC plus theory. So now one can actually come back from these Weil-Arakelov descriptions to an integral fundamental line, because I was saying here, if you work out what this volume statement means, it means that these two Z lines in the same R vector space are related by a factor which is exactly the leading coefficient, or rather, this is the cleanest statement here. So that means if you put this determinant on the other side, we get a fundamental line. So one can really, for this regular proper arithmetic scheme, one can write down an integral fundamental line, which is just these two determinants. And once you tensor this line with R, you get a canonical trivialization, because there was this canonical isomorphism between those. And the leading coefficient would, this conjecture for the leading coefficient would say that the image of the coefficient under lambda infinity is just the integral fundamental line, which has a unique generator up to sign, because it's just a Z line in some R vector space. So now the conjecture looks exactly like yesterday, like the Tamagawa number conjecture, where I have the fundamental line for a motive. But here I put all the HIs together. So, so if X is smooth proper of a number ring, then this fundamental line tensored with Q is indeed the product of the fundamental lines from yesterday over all I in all degrees that occur. And so you take somehow the total motive of the generic fiber, and this isomorphism lambda infinity is also a product of one theta infinities from yesterday. So the two conjectures are compatible, which is how we defined this factor in the first place. But we can really only define it if X is smooth proper, not for general regular X, because then the bad fibers will play a role in general. And so, so this conjecture with this correction factor is compatible with the Tamagawa number conjecture. If we make the conjecture in this form with this TC plus complex, then of course we have no a priori connection to periodic Hodge theory. We would have to show that this correction factor coming from the Tamagawa number conjecture is actually this explicit factor C infinity just given by these factorials. This looks hard, so we could only prove it in this case. But even for a number field where the local fields are not absolutely abelian, it looks hard. It might be doable with recent technology, but it's hard. But we don't need this to make a conjecture, right? We're pretty sure that our conjecture here is correct. So we need not worry about compatibility to the Tamagawa number conjecture. But this would be an interesting project to show that this factor is really equal to the C infinity. In other words, that this expectation is true. Yeah. So what this also means is that one can't forget about all these Weil-Arakelov groups. You can define these Weil-etale groups directly. This is already directly defined. And then you define these isomorphisms, again coming from regulator and period maps. And so you have a special value conjecture. So you can forget about all these groups I was telling you, and you can just make a conjecture using the fundamental line, just like yesterday. but to me, it doesn't look as illuminating as this Weil-Arakelov groups, to be honest. But one can basically forget about the Weil-Arakelov groups. So let me just say a few words how you would directly define these complexes. So what we do. So again, the key assumption is finite generation of etale motivic cohomology. And then the Artin-Verdier duality, which is known in many cases, for example, if X over spec or F is smooth, so then there's no assumption. And it will tell you that over X bar, I mean, the difference between groups on X and X bar is only two primary torsion stuff. So there's no difference, but the duality is cleaner over X bar because then the groups in higher degrees, bigger than 2n plus 1, they're simply dual to groups in lower degrees where they're finitely generated. So in other words, in higher degrees, you have co-finitely generated groups, just as I was explaining at the beginning. And so what we do is to get a perfect complex, we simply take the mapping cone of this map now. So we have a map from R home of this dual, complex with a dual twist into Q, mapping into this complex. So the Q maps to the Q mod Z here, and the fiber is a Z. And so the fiber would, or the mapping cone, would be a perfect complex of abelian groups. So this is how we define Weil-etale cohomology of X bar. And then the Weil-etale with compact support is again a mapping fiber, which is some perfect complex associated to the infinite places, which is basically some integral structure of the Betti plus space here. As you would expect, compact support involves a fiber to the infinite place. And so this is how we define these complexes. So all the maps, one has to check lots of details, but it's certainly not a very elegant way, but it would also work over finite fields, so one doesn't have to use the Weil group there. So it's a uniform way to construct this Weil-etale cohomology complexes. And so once we constructed those, we construct the Weil-Arakelov complexes by doing further mapping fiber construction. And so this is clearly not the final way to construct this complex. So we believe there is a different, a much better way using more K-theoretic ideas, but at the moment, that's the only thing we can do. And the special value conjecture looks quite clean in this with using these groups. So it's just these two statements here. Yeah, so okay, so let me just finish with this. I already mentioned it. One can prove that the conjecture is compatible with the Tamagawa number conjecture. So again, we expect this quotient to be 1 always, but we only know it to be 1 if n is less than or equal to 1, or x spec or f, where all local fields are abelian. But what this is good for is that it actually gives evidence for our conjecture, because we can translate known cases of the Tamagawa number conjecture to known cases of our conjecture, in particular for spec or f, where f is an absolutely abelian field. As I was explaining yesterday, for Dirichlet functions, everything's known. So in particular, Tamagawa number conjecture is known. So our conjecture is known for absolutely abelian fields. So it's just that statement here, this quotient is 1. Yeah, so maybe that's a good point to actually take a break. The topics I have left would be discuss the example spec or f in more detail, compatibility to BSD, and compatibility to the functional equation, and I'll do that tomorrow. Thank you.
Thank you very much for your nice and clear talk. Thanks, speaker.
Thank you.
So maybe will you say something about the TC plus complex tomorrow, or have
yes.
you?
Yes.
Oh. So Sujata has a question, please.
Yeah, Thanks, Matthias. So I had
Hi.
a couple of questions. One is there something more that you can say if you work with ZP or rings of integers over local fields, say periodic local fields, in this situation? And then the second question was, you had this running assumption throughout, or the finiteness of those cohomology groups for less than or equal to 2n plus 1.
Exactly.
What is known? For what n is something known, and so on.
Okay, it's
and
basically
references. I hope the references are somewhere, because there were a lot of things that you said, state of the art, current technology, etc., etc.
Yeah. It's basically my papers with Morin, which appeared in Documenta mainly.
Okay.
The finite generation is known for spec OF by Borel's work. And together with the motivic spectral sequence, because I'm not talking about K groups, I'm talking about motivic cohomology, for which there's a two primary difference. And it's also known for an arithmetic surface, so in other words, a curve over a number field where the Jacobian has finite Chow, right? So this is now known for many elliptic curves that Chow is finite, right? I mean, still not.
Yeah, and what about local case, the local QPs?
Well, I didn't talk about specific local statement here. What do you mean?
No. So for instance, you had all these statements where your model was over spec Z, right?
Yes.
So if you take things over spec ZP, then there are all these questions about the kernel of the Brouwer-Manin pairing and so on. So these have some applications there.
I'm ignorant about this. So, I mean, arithmetic geometry over local fields is not directly involved in this. So what this discussion covers is varieties over finite fields and arithmetic schemes over spec Z. I don't have anything to say about local fields. I mean, local fields come in when one wants to compute this correction factor, right? I mean, like, there's lots of periodic Hodge theory in there. But I'm not sure that relates to your question where you ask about the Brouwer-Manin pairing and so on.
All right. Yeah. Thanks, Matthias.
Yeah. Okay.
So are there further questions or comments in the audience here? Okay. Thanks a lot, Matthias. And
Okay.
see you tomorrow.
See you tomorrow. Yeah.
Good night.
Bye.